Hello, I'm Chris Seaton. I'm a senior staff engineer at Shopify, where I'm working on Ruby performance. I'm the founder of TruffleRuby, which is a very highly optimizing implementation of Ruby. I also maintain the Ruby bibliography at rubybib.org that documents research on Ruby. Today I want to share some existing ideas that TruffleRuby uses for how to implement objects in Ruby that we think could be applied in MRI or other implementations of Ruby. We'll explain where these ideas have come from and what their history is. We'll describe how they work in a high-level way, and then we'll show how TruffleRuby implements them, what it's able to achieve, and how MRI could do the same things. We'll then look further into the future and talk about what else could be built on top of these ideas. When people ask me about why Ruby is sometimes slower than other languages, the headline reason I give them is it's all about the what-ifs. Ruby implementations spend a huge amount of time asking themselves what if while they run your programs. For every add operation, it has to think what if it's overflowed. For every method call, it has to think what if the method has been monkey patched. For every line of code, it has to think what if someone has enabled tracing, and so on and so on and so on. There's a lot of work at the moment to try and reduce the cost of these what ifs. So there's mjit, JRuby, sorbet compiler, YJIT, TruffleRuby, and more all work towards this in some way. But apart from JRuby and TruffleRuby, they all use Ruby objects in the same way. They aren't yet solving the what-ifs for Ruby objects. And there are a lot of what-ifs associated with Ruby objects. We constantly need to ask, what if the object is frozen? What if the object doesn't have the instance variables that we expect it to have? What if the object is shared between multiple actors? The idea of object shapes that we're going to describe in this talk is a technique that tries to remove as many of these what-ifs as possible. Several people think that taking this next step will make other efforts to improve Ruby performance, such as mjit, the sorbet compiler, and YJIT, more effective. We'll see later on, it may also have some benefits for the space your Ruby program needs to run, so it's not all just about time performance. When we talk about Ruby objects here, we're talking specifically about objects with instance variables. We're talking about how these instance variables are stored inside the object. There's lots of other interesting aspects of objects, and we'll talk about some more towards the end of the talk, but for the big idea that we're talking about here in this discussion, we're talking about instance variables. For our purposes, a Ruby object is a bag of key value pairs. Unlike a Ruby hash, all the keys are symbols, and the key value pairs aren't ordered in any particular way. We can get and set these instance variables using the @ syntax, but we can also use instance variable get and instance variable set, and there are methods such as instance variables, which give you all the keys, and keywords such as defined, which tells you if a key is set or not. A debugger may give you similar tools to get and set instance variables. Ideally, we'd like to consider all of these syntaxes and methods and keywords as all being equally important and equally worth optimizing, so that people can use whichever they think is the right tool for the problem they're solving, without worrying about which is faster to use. It's really important to emphasize this point that in Ruby, instance variables conceptually live in the object. That is, they aren't part of the object's class or the meta class. You don't define them in the class, you just go ahead and use them. Even if you're using an attributes accessor, they're still just defined on the object. The class doesn't really know about them. Let's look at how objects and instance variables work today in a couple of Ruby implementations. Note that the code I'm going to show in this talk is significantly simplified for clarity and removes lots of the corner cases and optimizations that aren't really relevant for the discussion, such as class instance variables, embedded instance variables, and generic instance variables, which are all quite niche topics you don't need to understand to follow this. MRI, or CRuby, is a standard implementation of Ruby implemented in C. Let's look at MRI's data structures first. In objects, we have a reference to the class, a number of instance variables in the object, and then a reference to an array of values of instance variables. In classes, we have a hash of instance variable names as symbols to their index in the objects, so the index in ivptr. Now let's look at how MRI, what the code MRI uses to access these data structures. I'm going to focus exclusively on the fast path, or the happy path, that is taken when everything is working well, that is encountered most of the time by idiomatic Ruby code. There's also slow path or fallback code that handles everything else, but we won't go into that here. We can see that the code checks that the class serial is the same as the expected class serial that's been recorded on the last access. A class serial is the version number of a class. It's incremented whenever the class is modified. We then also have to check that the object has as many instance variable slots as required, because the object may not have the same size as other instances of the same class. We can also think of this in terms of pseudo Ruby code, if that helps us to understand. So to get an IVAR, we have a cache which is passed by the interpreter, and we have the receiving object that contains instance variable. We check that the cache's serial number is the same as the object's actual serial number at the moment, and we check that the expected number of instance variables is less than the number that it has. And then we can go ahead and read it. Otherwise we use a slow path. And the code for setting is very similar. Just instead of returning reading from ivptr, we write into it. And again, we have a slow path for writing. JRuby is Ruby re-implemented in Java. Unlike MRI's various JITs, it also re-implements how objects work from the ground up. What JRuby does is it makes a static guess of what instance variables it thinks a class is likely to have by looking in all the methods, including all the inherited methods, for all the variables that are referenced with the @ syntax. It then generates a new Java class at runtime to contain that many Java fields, so one per Ruby instance variable. These generated Java classes are shared between all Ruby classes that contain the same number of variables. Each Ruby class then has a map of instance variable names to their Java field equivalents. For the code to access these variables efficiently, JRuby uses a mechanism of the JVM called invoke dynamic for accessing these variables. That's quite a complicated, sophisticated VM technology, so I won't go into it here. We'll just sketch the effective result using Ruby pseudocode rather than going into the Java code. So for the JRuby version of VM get IVAR, we check that the cache's ID, which is like a class serial, is the same as the meta class's real class's ID. And then again, we can index into the object, and again, there's a slow path. A benefit of this approach is that because the number of instance variables is allocated statically, we only need to check the object's classes as expected. We save that check that MRI was doing, that the object has enough storage space for the instance variable. The object class's identifier is compared against the cached value. Unfortunately though, this is 3 hops from the object. We'll have to hope both the object and its meta class and its logical class are all in CPU cache for this to be efficient. Another limitation is the guess that this has to make. If it guesses wrong due to variables or classes being set up by some kind of meta programming, which of course is very common in practical idiomatic Ruby, it falls back to a slower path for reading and writing instance variables. This is also the way that Rubinius worked historically. Now there's arguments for and against this trade-off that JRuby's made, but we think we can get the best of both worlds using shapes, so we don't have to worry about the trade-off. Let's talk about the history of shapes, the history of this big idea. The history of object shapes goes back to the Smalltalk and Self programming languages. You may have heard people mention these two languages quite a lot when we talk about language design in history. People are always very keen to say their language is inspired by Self and Smalltalk in the same way they're keen to say it's inspired by Haskell. And Shape's a great example of a technique that we owe to the researchers working on these languages quite a long time ago now. We don't talk about history enough in our field, so let's take the opportunity to take a look at the original papers for this idea. So the starting point for all this was Smalltalk. Today we think of Smalltalk as being a very simple, elegant language, but it's interesting that at the time, some people argued it was far too complicated. And as a reaction, a simpler language called Self was developed that was intended to increase developer expressiveness and productivity, or maybe what we'd today call in the Ruby community, developer happiness. They were optimizing for developer happiness. One of the improvements for simplicity they added was prototypes instead of classes. And that's prototypes as in the way JavaScript objects work, if you have experience with JavaScript as well. So JavaScript doesn't have classes, it simply has objects which have properties, and to inherit you point to another object as your fallback for reading properties if they're not in the object you directly access. Ruby does have classes, but as we said, the methods and instance variables in individual instances don't depend just on the logical class, so Ruby is somewhat more like prototypes than pure objects. Initially, however, Self was a less efficient language, and that's a cost for prioritizing developer happiness. And there's possibly a parallel with Ruby here. The language that prioritizes developer happiness unfortunately pays some cost in performance. But the good thing is this motivated researchers to find ways to make Self more efficient and overcome the costs they introduced with the design that they wanted. Now, this research led to some major developments that continue to be very influential today, such as polymorphic inline caching. I won't explain this technique here, but it's key to the high performance that Java and JavaScript have today. TruffleRuby uses a novel form of polymorphic inline caching called dispatch chains to optimize Ruby's metaprogramming. So the idea is still being iterated on and developed today. The major development we're interested in here is shapes, or as they're called in Self, maps. Or sometimes today in the context of JavaScript, they're called hidden classes. We'll use the term shapes here because of maps could be confusing with hashes, especially if you're coming from a Python background or something like that. So we'll call them shapes, but the original researchers called them maps. Their idea was to separate the keys and values of instance variables. The keys would go into the map, which would give you the index of the values in the object. The object referred to the map, so you can use that to find which value to read for a given variable. Note that the part of the original motivation for the idea was actually space, not speed. Because when they switched to prototypes, they realized all objects had a full set of the keys as well as the values, and they realized that by separating them out, they no longer needed to keep all those copies because of objects with the same keys could share them. That's the history and how the original researchers described it. We'll now try to give a full explanation of the big idea using terminology and diagrams that are a bit more concretely relevant to Ruby. We'll have these things that we call shapes. A shape will give a mapping from instance variable names to their index in all objects with that shape. We'll draw the shapes with dashed lines, and we'll draw objects with full lines. So the object is on the left here and the shape is on the right. The object references a class, which isn't important here, and it references the shape. So there's an arrow from the object to the shape, and the class and the shape pointers together represent the header of the object, would say. The object then contains just the values, and the shape contains this mapping from names to indexes. So it doesn't contain the value of instance variables, it just contains an index saying where to find them. Every object has a shape. So objects are initially created with a special empty shape, for example. When an object is given a shape, it is also given the right amount of space that this shape requires. So it may require resizing the object or using a separate data structure such as an off object array to store if the shape needs to be, if the object needs to be increased in size. How the space in the object is used is described by the shape. So if you think of the shape as metadata, something that describes the data and how it can be used, or you can think of it as a schema from a database context. To get an instance variable, you conceptually looking up the index in the shape and then reading that slot from the object. So this isn't how it works in practice, but this is how it logically works. So we get the index by looking in the shape. If we want to read the instance variable name, we get its index out the shape, and then we can index the object and read out that value. To set an instance variable that has been set before, so that the object already contains, and not a new instance variable, one it already contains, you're conceptually doing the same, but now you're writing the value. So you get the index by looking at the object's shape, looking at the instance variable by name, that gives you the index of within the object, and then you can write within the object to set the value. But that only works for instance variables which have already been set in the object in the past. We'll cover what happens if you set an instance variable which hasn't yet been set in a minute. So how is this different to what MRI is doing? Because it seems sort of similar. Well, the key differences start with that shapes are immutable. And we know that immutability is often a good way to do design software. This means that if you knew what the shape was at any point in the past, then you definitely know everything about the shape for the rest of time. You can hard code assumptions about it. Second, shapes are divorced from classes. Two instances of the same class may have different shapes. This means that objects don't have to change behind your back because other instances changed. So because shapes are immutable and because shapes are separate from classes, objects don't get changed from afar because someone else did something that happens to be an instance of the same class. Right? They get to look after themselves, and nothing ever changes unless you decide to change it. And all this means that you can compare the shape of an object against the shape you expect, and that's probably going to be a simple word comparison on your processor, and then you know everything you need to know about the object. The shape cannot change in the same way that class's instance variable change in MRI. Now before, when we did setting an instance variable, we said that it had already been set in the past and we were simply giving it a new value. If you're setting an instance variable that hasn't been set before, now you're using something that doesn't have a comparison in MRI, which is called transitions. Shapes also know about what shape you get if you were to add, remove, or change some instance variable in the shape. So here, this shape knows to transition to the shape on the further right when a height variable is added. So there's now a new arrow that goes from the shape that the object used to have to a new shape if the height variable is added. So to add the height instance variable, we don't modify the existing shape, we create a new shape. Okay? And we can record the fact that this is the new shape we created when this variable is added. And here we get a graph over time describing all the transitions the program makes. So as your program runs, you'll build up a big graph of how to get to different shapes from the shapes you started with. Transitioning an object isn't a slow path operation though, right? This isn't something that if it happens is a disaster performance. It can be done quickly using just information from the shape we already have. So again, this is conceptually, it actually happens much more efficiently in practice. We can get a new shape by looking at an object, looking at its shape, looking at the transitions out of that shape and saying what happens when we add a height variable, and that gives us a new shape. And that shape probably already exists. If it doesn't, it can be generated. Then we can get the index from that new shape, and then we can modify the shape to have we can modify the object to have that new shape. We possibly may need to resize it, but we'll try to amortize that. So we won't resize it by 1 every time, we'll probably double it or something like that. and then we store the instance variable into that slot in the object. So that's not a slow path operation. That's not something where, oh, it's all gone wrong, we need to fix it up. It's fine for that sort of thing to happen as the program runs as normal. Now, this all comes together for the best effect, to get the most out of it when you combine it with compilation to machine code. So a just-in-time or ahead-of-time compiler. Machine code can include hard-coded values, and that's part of the magic of it. So we can hard code the address of the object shape to compare against. And we can hard code the index used based on that. Now we can do that machine word comparison and a machine read. If the comparison fails, we'll run some other slow path code far away that we don't have to worry about most of the time. And the great news is these two operations, the compare and the read, can more or less run at the same time on a modern processor, because processors can predict whether a branch is going to be taken or not, and we can write this branch in such a way that we make it pretty clear to the processor this branch isn't likely to be taken. Just go ahead with executing what's after it. If it turns out later the branch was taken, then we'll fix that up, and that's a bit of a problem, but we can fix that up. But in most cases, the read can go ahead while the comparison is done. So again, this is pseudocode, but what we'll do is we'll run some slow path unless the object shape is what we expect. So we just read the shape, compare it against a number, and then we can do the read again with just a constant number. And those constant numbers, they don't have to be read from some side data structure, right? So in a YARV instruction, you often have data and you have to read that from memory. It can actually be part of the instruction stream encoded into the actual machine instructions. So how does TruffleRuby do shapes? Can we transition this from talking slightly in the abstract using some Ruby pseudocode to showing what it practically does? The way that TruffleRuby implements shapes is described in the research paper, An Object Storage Model for the Truffle Language Implementation Framework. That's written by Andreas Voss and others. We're going to show what TruffleRuby does by showing an internal graph data structure that it uses to understand and optimize Ruby programs called the intermediate representation. We're going to use a tool developed by Shopify called Seaton to visualize these graphs. Now, I appreciate these graphs might be a slightly new concept to some people, and they may look a bit intimidating. And they're also graphs from a production compiler, so they're not designed to be easy to understand, but I hope they are. But it's good because we can show you this using actual compiler production data structures. So this is a compiler graph or intermediate representation from TruffleRuby, from the Graal compiler that TruffleRuby uses to understand your Ruby program. In this fragment of a compiler graph, the nodes represent operations. So when I say node, I mean the boxes and the diamonds. They represent computation of some kind or a value of some kind. And the thick red lines represent the control flow. So if you have a thick red arrow from one box to another, that means that box has to execute before the other one does. It means the order in which to execute the program. Now the thin green lines represent the data flow. So data comes out of things and heads to other things. So if we look at node 524, the equals, it's got 2 data inputs and 1 data output. So it takes in 2 things to compare and it produces a result. So this is a flowchart version of your Ruby code with the implicit parts of Ruby made explicit. And that's how the compiler works. It takes things which are implicit in Ruby and it makes them explicit so it can reason about them. Now here we can see an instance variable read is being done by loading the shape. So node 521, it loads the object shape. Load field, dynamic object, shape. It compares it against a known shape, so there's a comparison 524 against a known shape, so a constant value 518. It then guards, which means it jumps to a slow path if the comparison fails, and then it loads a known location within the object, which is primitive 1, which is one of those slots. In the machine code, we can see that comparison against the expected shape jumping to the slow path if they're not the same, and then loading the variable. That's 3 machine instructions. So the first machine instruction, if you're not aware, in Intel processors, a single instruction can load memory as well as do some arithmetic. So what this is saying is comparing reading from the object, which is RAX in the register RAX, and then times 8 plus 0xc is saying read the shape within it. It's just a field within the object. Then we compare that against an expected shape, which we can hard code into the machine code, right? So it's not reading it from some memory, that's hard coded in. We then say if they're not equal, then go off to some slow path, and then we say move the indexed value from the object into a register, and then we can keep doing whatever we like. So just 3 machine instructions, and you can also look at the graph to understand the logic behind it. In this fragment, we can see the code for setting an instance variable which already exists in an object, so no need to change the shape here. And as before, when we looked at that pseudocode, it's the same as the getter, except the last 2 operands are now the other way around. We write rather than read. So before we had a load field, primitive 1, now we have a store field, primitive 1, and it takes a value to write in. And again, the machine code looks exactly the same, apart from now the last 2 operands the other way around. So instead of getting a value out of the object and putting it into a register, we're now taking it out of a register and putting it into the object. So again, it's just 3 instructions. So 3 instructions to do an instance variable read, an instance variable write. And I think that's pretty optimal. It's hard to imagine a way that could be done much more efficiently. Let's consider a slightly more complicated case. If the instance variable doesn't already exist, we'll now be changing the shape. We're going to follow the transition from the current shape to a new shape. As everything in the shape is hard-coded, remember we said if you know the shape, then you know everything about the shape forevermore, so is the transition. That's hard-coded as well. We now just write the new shape as well as writing the value. So in this, if we have some Ruby code that writes a new instance variable that hasn't been written in the object before, remember it's not about what the class has seen before, it's what that individual object has seen before. We now just need to write the field in. So we're writing to primitive 2 now rather than primitive 1, because this is a second instance variable into the object. And notice that we now store a new shape into the object. So the only difference here for adding a new instance variable is just writing a new shape. And again, that write can happen pretty much in parallel with other things, because Intel processors can pipeline things very well like that. So it's not a slow path operation. It's not something that has to happen offline. It's something you can just keep going and flow through. Now we can start talking about some of the more advanced ideas for applying shapes in Ruby, as well as shapes in TruffleRuby mapping instance variable names to their storage location with the objects. We can also map their types, so we can include extra information as well as the index inside the shape. In MRI at the moment, all instance variables are stored as full value objects. And that effectively means they're a void pointer, so just a machine word, and they all get stored in the same way. A small integer must be tagged to be stored as a value, and so to be stored as an instance variable. So if you have a number, you have to do something to it to make it into a value that you can put into an instance variable. And then you have to untag it when it's retrieved out of the instance variable. Now, compilers that are optimizing would like to avoid tagging and untagging. So if we note in our shape that an instance variable is always going to be an integer, then we know we won't have to tag values going into it or untag them coming out again. If the variable becomes something else later on, we'll transition the shape just as if we were adding a new variable. So if our shapes now contain typing information, such as that A and B are integers, then we'll add that alongside the index. And if someone wants to store a string in A instead of integer, we'll have a transition that says change the type of A to string, gives you this new shape. We can see this working for real in TruffleRuby. This add routine is in an object where the two instance variables are always small integers. When I say small integer, I mean what we used to call a fixed num historically, but that's now an implementation detail of Ruby. We can see that the generated machine code reads the values from the object, having checked the shape, but it doesn't do any work here to untag or unbox. Unboxing is Java's version of untagging. It just uses them, right? So it reads from the object into ESI and EAX, which are two registers, and then it does an add operation on them, but it doesn't untag them. Normally you'd have to shift the value to get rid of the tag data. And this is because the shape told the compiler these variables had the small integer type, so it knows when they come out that they're untagged, and it can do whatever it needs to from that point. It can just use them, as it is in this case, or it might want to tag them again to pass them on somewhere else. When we checked the shape, we also checked the types. Right, so that one check covered both variables at the same time and checked covering their types. Because of the shape includes the type information of all the variables, so just checking the shape checks all the types at once, and also checks the layout of the object. And also that shape check is already there for the layout, so we get it for free for checking the rest of them. So when we checked this shape, we also checked the types, and that one check covered both variables at the same time. So now we're getting code that looks more like it came out of a C compiler than that it came out of a Ruby compiler. Getting even more inventive, what else could we move into the shape? There are more properties of objects that are isomorphic to instance variables, so look a bit like instance variables. For example, the reference to the class and the frozen state. If we stored these in the shape, then we'd get two advantages. First, we'd have one less word and one less bit to store in the object, reducing space. Second, we could collapse three kinds of check. So the class, checking the class for the method calls, checking the frozen status, and the instance variable write check into just one, just the shape check. TruffleRuby already folds the frozen check into the shape. Looking back at our setter example, we didn't see any code to check if the object was frozen when we wrote an instance variable. But the check is there. This expected shape is statically known to not be frozen. If the object was frozen, it wouldn't have this shape. It would have a different shape, one that had been marked as frozen. This is a great example because it shows that we can completely remove the overhead of a Ruby language feature. It's the same code as if Ruby didn't have the idea of frozen objects. So we've got that language feature but not having to pay for it. TruffleRuby doesn't fold the shape into the class. Doesn't fold the class into the shape at the moment, as the developers think that conflating the method call class check and the instance variable check may not be sensible. You'd possibly create polymorphism in method calls for the unrelated reason that objects have different instance variables. So two objects which you could dispatch the method call in the same way, you'd be looking at differently just because they're different instance variables, which is unrelated. TruffleRuby also uses the shape to mark objects as being shared between threads and activates locks for synchronization if this is the case. And the same idea could be used for rapture checks. What other ideas are there out there for objects? In general, a lot of Ruby optimization effort at the moment is going into optimizing the execution model of Ruby. So mjit, yjit, and the sorbet compiler all swap out the interpreter for just-in-time compiled machine code, but they leave the rest of the virtual machine as is. So mjit and sorbet compiler generate what is effectively a C extension for your code that you then plug into standard MRI. And yjit is doing something roughly similar, but it doesn't work at the level of whole methods. I would suggest that efforts at optimizing Ruby do need to look at objects some more. I think there's exciting ideas that people at Shopify are working on, such as concurrent compaction for the garbage collector, variable width allocation of objects, and novel garbage collection ideas. TruffleRuby does some incredible optimizations for hashes and arrays, allowing them to specialize for their size and for what they contain. TruffleRuby also has a very powerful optimization called partial escape analysis that allows objects that only use within small groups of methods to be virtualized and never really allocated on the heap. And because of objects, especially hashes and arrays, are so prevalent in idiomatic Ruby, getting rid of them rather than just trying to use them as they are but as efficiently as possible is a really key thing to try and do in my mind. Practical recommendations. So my headline practical recommendation is let's implement object shapes in MRI. I think the complexity is actually relatively low, and it may even have an immediate speed up benefit for the current MRI interpreter because it's reducing checks that the interpreter has to do as well. But it won't be quite as effective because remember we said that it really comes out when you're using a compiler because you can hard code things. And it'll certainly help MJIT, YJIT and sorbet compilers they continue to develop. TruffleRuby shows the idea works well, and I think there's also some exciting possibilities for building things beyond that, which we already went through. Such the TruffleRuby paper on it that I mentioned talks about more practical implementation details if you want to know how to implement it, and it also shows the performance it achieves compared to a couple of other methods of implementing objects in Ruby. I don't think there's any major open problems to resolve. I think it's just an engineering challenge. I really just think it needs someone to build it using what we already know and using that chain of research going back to the early 1980s that we can follow, that is proven that we can implement in Ruby. And as we showed when we talked about the history, Ruby is already philosophically aligned to the languages where it came from, and that the problems it's trying to solve, both in terms of developer happiness and optimizing for that, but now trying to recover some of the performance, we're aligned to what Self was trying to do, so it makes sense to keep using their techniques. That's all. Thanks very much for coming to listen to my pitch for object shapes in MRI.